University. She was a student in Bulgarian in the American University in Bulgaria. Then I think she was in the East European University in Budapest. She got PhD in MIT or where?
Johns Hopkins.
Or Johns Hopkins. A postdoc in Yale, but now she's there. So from such a CV, you see that she's quite young, but quite well educated. And I hope in the near future, very famous. So your talk, this is tropical geometry and commutative algebras for semirings. Okay, please.
Thank you for the invitation to speak here in front of so many Bulgarians and other people interested in my topic, and for the wonderful introduction. So I'm going to give this talk as sort of an advertisement for the field. I'm not assuming anyone knows what tropical geometry is. So I'll try to keep it very a low requirement or prerequisite. This will be joint work with the two of my co-authors, Daniel Yu from the Rainy Institute and Nati Friedenberg from, who's my postdoc here at Tulane. And this work spans over many papers, but I'll try to reference them properly. So without further ado, what is tropical geometry about? Usually what algebraic geometry does is looks at objects that look like this one on the left, which is this a curve. And if we want to study those, we'd like to instead study their combinatorial shadow, which is the tropicalization of such a curve. So instead of instead of studying algebraic objects, we study these combinatorial objects. And they're very nice combinatorial objects. There's many theorems about them. So in particular, they're polyhedral complexes that are finite, pure dimensional, balanced, and so on. So how do we do that? Well, we want to find a map that goes from my algebraic curve to my tropical curve, or my algebraic variety to my tropical variety. So let's first very quickly look at what we do in algebraic geometry. Well, if I have a curve or I have a variety, then it's defined by an ideal that it lives in a polynomial ring. In this idea, we have polynomials, clearly. And what the geometry is, well, I'm looking at the zero locus of each of the polynomials in the ideal, and this is going to cut out my variety. Now, what happens tropically? So how do I go from this usual setup that most people learn and love to this other tropical setup? Here's what we do. There's one thing I didn't tell you, is that my field that I'm going to discuss has a valuation. So for me to go from a point on the algebraic curve to a point on the tropical curve, I'm going to apply a valuation map. Okay, so very quickly, what is this? So this is a map from the field to the real numbers plus infinity, or usually from the non-zero elements of the field to the real numbers, but I can extend this such that the product now becomes an addition, so addition of real numbers. And if I'm adding two elements and taking the valuation, this should be bigger or equal to the minimum of these two elements, the valuations of these two elements, and 0 will go to infinity. So this is my map. This is a valuation. I can apply it coordinate-wise here to go from a point of the curve to the point of the tropical curve. Now, I'm going to denote the set very suggestively by T with plus and times, where here the plus, we saw that it's going to be something different. It's going to be minimum, and the times is going to be usual addition of real numbers. So this will be my tropical semifield. the set with these two operations. So what happens to the algebra? I'm interested in understanding the underlying algebra here. The underlying algebra, well, I will, if I can do something to the points, I can do something to the polynomials as well. So what is my a tropical polynomial now? It's going to be something that lives in, sorry, my tablet is being funny as usual. It's going to live now in a polynomial semiring over with coefficients in this new place that I just defined. And what trop f is going to be the minimum over all monomials of the valuation of the coefficient of each plus x dot u. So this is what it's going to look like. This is what I'm going to refer to as a tropical polynomial. If I want to do this for the whole ideal, I just need to do it for each polynomial in the ideal. So trop I is, sorry, the ideal generated by these tropical polynomials. Okay, so this is how the algebra changes. Okay, so that's what happens to the variety. If I want to talk about the tropical variety here, what is this? Now, before I was taking the zero locus of some polynomials, can I do this here? The answer is not quite. And of course, I want this to be consistent with this picture and to get the same thing. So what do? I actually find a tropical analog for vanishing, which is I'm going to consider here all points in t to the n such that f of p vanishes tropically, which means is either infinity or the minimum is attained at least twice. Either infinity or the minimum is attained twice for two monomials. Why is this a good replacement for the vanishing condition? Because two things, one thing minus another thing is zero if those things are the same. So this is sort of an abstraction of this. So this is what happens in tropical geometry and how we define these tropical objects. Now, what's the motivation for doing any of this? Well, the motivation is there's a lot of applications to algebraic geometry. There's been a lot of tropical methods used in studying moduli spaces of curves, enumerative geometry like computing Gromov-Witten invariants, Brill-Noether theories, mirror symmetry, and so on, but also outside of algebraic geometry, such as mathematical biology, economics, neural networks, and others. So these methods seem to be very useful in other areas of mathematics as well. Now, what are the pros and cons of studying instead of my algebraic objects, these tropical objects? Well, the pros are that there's a new set of combinatorial tools, because now I'm working with a polyhedral complex. I know things about polyhedral complexes or metroids or something like that I can use, but there are also cons to this process. We do lose a lot of information because, as I said, this is a combinatorial shadow of the original, and even if it remembers a lot about the original algebraic variety, it is not everything. And most of the information that we lose is algebraic information. And it makes it hard to work in higher dimensions. In higher dimensions, we sort of lose track of all the combinatorics. So our sub-goal, or at least the sub-goal of my research, has been to salvage enough algebra to create an intrinsic theory so we can talk about tropical varieties as varieties of some tropical polynomials and work with those, not with the algebra of the original variety. So a couple of remarks. I introduced this tropical semifield, T, which was as a set, the real numbers with infinity and two operations, minimum and addition of real numbers. So this is a semifield. In particular, it's additively idempotent. What does that mean? It means that for every element, if I add the element to itself, I'm going to get the element back, because addition is really minimum here. And there is no negative sign. So this is why it's a semifield, not a field. So I cannot, the addition operation, which is minimum, is not invertible. And this brings to a lot of problems. In particular, the polynomial semiring is not cancellative. It's not the unique factorization domain, and so on. So this will bring a lot of problems later if we're trying to do what we usually do in commutative algebra. So we'll try to understand a couple of things for this talk. One is quotients. And why do we want to understand quotients? Because they are the coordinate rings of affine varieties. So what that is, if you're not an algebraic geometer, something that looks like this, it defines your algebraic variety, affine algebraic variety. The next thing is prime ideals. Why? Because they are irreducible things. They define irreducible varieties, and they're somehow the building blocks for the theory. So the reason why I have a question mark is that I want to make the point that we probably don't want to understand ideals necessarily, but perhaps something else that is prime. And the last thing is I'm going to talk about dimension, how we define dimension in this case, and how consistent it is with the algebraic theory that we have developed. So this is sort of my plan for today. All right, so so as I said, first thing would be quotients. So in the ring case, if I want to define a quotient by an ideal, what do? I really quotient by an equivalence relation. So what is this equivalence relation? It is in fact this one, CI. I'm going to set everything in the ideal to be congruent to 0, and I'm going to quotient out by that. So in a sense, I can think about this ideal here as the kernel of this equivalence relation, which is a congruence. Congruence means an equivalence relation that preserves the operations. And the reason why we never bother with these writing out these congruences in a commutative algebra is because there's a one-to-one correspondence between ideals and these things. Now, why am I telling you all this? Because in the semiring case, this is not the case. This part. What do I mean by this is that because now I can say take a polynomial ring into semiring into variables, and I can quotient out by the congruence relation x congruent to y. And this is going to be isomorphic to a one variable polynomial semiring. So this is a legitimate congruence. But the kernel of this congruence is trivial. What I mean is nothing here is really congruent to 0. So nothing other than the 0 is congruent to 0 because we don't have a minus sign. So understanding the kernels of these congruences, namely the ideals, is not necessarily going to give us a good enough picture to understand algebra. So let me quickly go through what happens when I try to do multiplication with these elements in a congruence. So instead of A congruent to B, I'm going to write A comma B, so that it's more readable. So I'm going to do this for pairs. One thing that we notice that if I'm living in a ring and I have a pair in this congruence, then this is in the congruence if and only if a minus b comma 0 is in the congruence, because for rings I have negative sign, which is if and only if a minus b is in the ideal. And now I'm just going to write this out, what it means for me to take this product. And I just use what I wrote above to manipulate this. This is the first, first I wrote them as with minus and pairs with 0 as the second coordinate here. Then I opened the parentheses and multiplied. And then, as I said, this is if and only if this without the 0 is in the ideal. And if I keep doing this, I end up with the last condition here. So this is what the product is. Now, this might not be interesting for rings, but in fact, I can use this to model something for semirings. Now, if I'm going to use this to define something which is called a twisted product, which is not really a new operation on pairs, but I can do that. And then I'm going to declare that C is a congruence on R, and I have two pairs, then the twisted product will be exactly modeling this situation. Okay, so every congruence is closed under this operation. So I'm not doing anything funny here yet. So yeah, so using this, I'm going to define what a prime is. So if R is a ring or a semiring, we all know what a prime ideal is. So if P is a prime ideal, if I have a product of two elements in the ideal, then at least one of them has to be in there. Now, what happens if I want to define prime for a congruence? I claim that this is going to be my definition. This is by from me and Daniel. It's our definition. So P is a prime congruence of R if whenever I have this twisted product to land in my congruence, then either of the pairs is in the congruence. So if I actually am working over a ring, this recovers the primeness, but it is more interesting for semirings. Now, of course, you might be asking, okay, well, you gave us a definition, is this any good? And here's some evidences that this is good in a way. So if R is an additively idempotent semiring, like the ones that we're interested in, then P is a prime congruence if and only if the quotient is cancellative and P is irreducible. Now, the intuition comes from commutative algebra, where every prime ideal has this property. And by cancellative here, I mean if I have AB equals CB, then either B is 0 or A is equal to C. This is what I mean by cancellative. Here by irreducible, I mean if P is equal to the intersection of two things, then P is A or P is B. That's what I mean. Okay, so at least intuitively, this sort of matches some primeness conditions that we hope to have from commutative algebra. Okay, so we actually have another theorem here that says that I can replace this irreducibility condition by something else, which is the following. If R is an additively idempotent semiring, then in P is a prime congruence if and only if the quotient is cancellative. So this is the old condition, and it's also totally ordered. This doesn't necessarily happen for, well, this doesn't happen for prime ideals, but it turns out to be very useful and very neat. So the primes of the polynomial ring because of this condition, the primes of the polynomial semiring and the Laurent polynomial semiring with coefficients, say in the tropical semifield, can be described by matrices. And they're related to monomial orders because the quotients are actually totally ordered, as we saw. And I want to give you an example of that. Here's my example. I'm working now with a prime, which is going to be defined by this 2×3 matrix. And this is going to be a prime over the Laurent polynomial semiring with coefficients in B. I didn't define B, so I'm going to do it right now. B is going to be the set of two elements. As I said, this is the only finite semifield, 0 and 1, and it's almost like the field on two elements, except for 1 + 1 is 1. So we have that. Everything else adding 0 to 1 is as you would think it works. So this is the Boolean semifield. This is my way of ignoring coefficients. So if I look at a prime congruence on this polynomial semiring, Laurent polynomial semiring in 3 variables, I know from my theorem before that the quotient is going to be totally ordered. So these two monomials, I'll be able to compare in the quotient. Or at least the images of these two monomials will be comparable in the quotient. So how do I do this? I look at their exponent vectors. So here I have 2, 3, 1. So 2, 3, 1. And then for the other 3, 1, 2, 3, 1, 2, I'm going to multiply them by the matrix. I'm going to get two vectors, 2, 3, 0, 1. I'm going to subtract them. And because, and now I'm essentially comparing them lexicographically, if you prefer that, which means here that M1 is bigger than M2 in this order, which is the order induced by addition on the quotient. So before I sort of switch to the next topic, are there any questions I can answer? Okay. In that case, all right, so I gave you some definitions and I said, oh, here are my primes, they follow some good, at least in my opinion, intuition from commutative algebra. What good are they? Do they actually pick out any geometric information? And so this is sort of my justification. I'd like to talk about the fact that they compute dimension in various cases. So dimension theory, we're interested for the rest of this talk in the case when R is an additively idempotent semiring. Think about our favorite one, which is going to be this. And I'd like to talk about how we define dimension. Of course, you can define it in the usual case in terms of prime ideals, I mean, crew dimension. So here I'm going to do it for prime congruences. So this is also a definition due to Daniel and I. So the crew dimension of R is the number of strict inclusions of prime congruences in a chain of maximal length. Okay, so one interesting thing potentially to point out, while polynomial rings behave better, polynomial semirings don't, and they are, for example, not catenary. So not every maximal chain will have the same length. Now, here are some examples. I just introduced this Boolean semifield, which was the set of two elements here. The dimension of this will be 0. However, with this definition, the dimension, for example, of the tropical semifield is 1. And we're not used to having dimension, positive dimension for something that has the word field in it, but this one does. There is why is this dimension 1? Because there's a unique congruence that sends everything that's not infinity to 1. And here we have this congruence, A is congruent to 1 when A is not 0, and that's why we have dimension 1. The dimension of the polynomial semiring over B is 1, which is good. The dimension of a polynomial semiring over T is the number of variables plus 1, and this is because the dimension of T is 1. And you can compute these by explicit computation using this thing that I introduced, that primes correspond to matrices. We can exploit that to construct an explicit chain. Now, this is all very nice, and we would ask, is this true in general, or this is somehow very specific to these two semifields that I picked? And the answer is, it's actually true in general. So if R is any additively idempotent semiring of your choice, then the dimension of a polynomial ring over in n variables over with coefficients in R is a dimension of R plus n. And I want to just note here that the proof is very different from the classical commutative algebra proof, because we do pass to the semifield of fractions of R, which has the same dimension as R, and then we work with chains there, which is something that we cannot do for rings, because the field of fractions of a ring is dimension 0. So it's quite a different flavor of proof. Now, the next thing I want to say is that just a brief comment on something that is probably painfully known to people in commutative algebra, that if R is a Noetherian ring, then this is true. So the same statement here works for Noetherian rings, but otherwise the dimension might jump. So in a sense, additively idempotent semirings seem to be behaving as Noetherian rings in this case, in this sense. And of course, before I do this, of course, the question is, okay, well, it's nice that this works with congruences, but perhaps there's a question, why can't I do this with ideals? In the semiring case, previously, I said, if I'm working with quotients, I need a congruence, not an ideal, because that doesn't work very well. But here I don't, at least not a priori, work with quotients. So why not ideals? And the answer is, there's a paper from 20-something years ago that says that if we define dimension in terms of ideals as the longest chain of prime ideals, then the dimension of a polynomial semiring in one variable, even over B, where the coefficients are either 0 or 1, is infinite. So this does not capture anything. And this is why you really need congruences here. Okay, so this is part of what I wanted to say about dimension. So I'm going to make a little bit of a turn here and talk about points of tropical varieties. And we'll see how we're going to connect this to dimension, more local things and others. So anyway, so let I be an ideal of the tropical polynomial semiring. What is the variety of an ideal? Well, I knew before I defined what the variety of an ideal, an actual ideal is once you tropicalize it. So what I talked about before is the variety of trop I, but now I'm already given this tropical ideal, and the variety is going to be all points for which every polynomial attains its maximum or minimum. I am really a max person, so it doesn't matter what you use. It's a choice. Attains minimum at least twice, or it's just the 0 polynomial. That's what this means. And I can define something similar for congruences. So I can talk about the variety of a congruence. So the variety of a congruence is going to be the set of all points in T to the n, such that f of a is g of a for every pair fg. So remember, this is what this means. F is congruent to G in this congruence. So if I do this, there is a natural question which says, what can we say about the varieties when P is prime ideal or a congruence? And again, we are interested in understanding irreducible objects. So this is a natural question. What really does this variety look like? Okay, so here's a theorem which says that if I have a prime congruence or a prime ideal in the tropical polynomial semiring, then the variety is either empty or is a point. And in fact, for this part, if P is a prime ideal and P is tropical, which means I'll define it later, but it means that there are some extra properties for this prime ideal that they're combinatorial. So it's not just any prime ideal, it's a little special. Then this is really saying this is a sort of a Nullstellensatz statement. Then P is the whole thing. So there's a weak Nullstellensatz statement for tropical ideals. Yeah, so this is very surprising because now my only, in a sense, the smallest, the biggest irreducible thing in the setting is a point. So this is surprising and disappointing. But if we can treat prime congruences as points now, perhaps there's a question about what happens locally. Can I talk about a local ring at a point and what is the dimension of that? And the answer is I don't quite want to think about a local ring here. I want to think about completions perhaps and take a more analytic approach to this. So if I look at convergent power series at a point, and by point I mean a prime congruence, then I can, this is some local object, and a crude dimension in commutative algebra captures the dimension of these local objects. So we get the same thing here. And we have a part of the work that I did with Nati says yes, that if P is a congruence with trivial kernel for technical reasons, then the dimension this local thing, this convergent, this semiring of convergent power series, it's not just the set, but the semiring, is in fact picked out, and it's the same as the dimension of the, in this case, coordinate ring of this toric variety. So this is not just true for coefficients in T, but the statement's a little different and involves the rank of the residue semifield, and so on. So it's a little bit more complicated, but this is sort of a corollary of our work. So we were happy to find out that this actually works out as expected. And the second question that is perhaps very natural here is how does this, okay, so locally this dimension works out as expected, but what about the dimension of the tropical variety? Do we pick it out? So we pick out some algebraic dimension, but does it have anything to do with the geometric thing? So for this, I want to say a couple of things. So we know in algebraic geometry that the dimension of the variety is the crude dimension of the coordinate ring. And there's a theorem called the structure theorem for tropical geometry or for tropical varieties that says that the dimension of the variety is the same as the dimension of the tropical variety. Now, the tropical variety is a polyhedral complex, but it's pure dimension. So pick any maximal cell, and the smallest dimension, the smallest dimension of the affine space that it lives in is the dimension of this polyhedral complex. And these two numbers happen to be the same. And of course, here's the natural question: do we have something like this tropically? So this is a geometric object. It has a dimension. We can perhaps talk about like a coordinate semiring, which is my polynomial semiring quotient by something, a congruence perhaps. And are they the same? So there's actually two questions here, this one and this one. So let me try to answer this for you. In fact, the answer is yes. So let me tell you how that works. So if we have an ideal, an honest ideal in a polynomial ring, then we can define this ideal that is the tropicalization of each polynomial. And now this lives in Tx1, xn. So now instead of me writing I, am going to just say J. If J is an ideal now in the polynomial semiring, I'm going to define something called the bend relation for a polynomial. And I'll give you an example. So I'm going to say that my polynomial is going to be congruent to itself minus a monomial, with one monomial removed. And I'm going to do this for all monomials. And then I'm going to take the congruence generated by all of these bend relations. These bend congruences were introduced by Jeffrey and Noah Siracusa in 2016 in their way to construct tropical schemes. So let me give you an example of what I mean by these. So if I have G to be the polynomial x plus y plus z, the bend of G is the set G congruent to x plus y, congruent to x plus z, congruent to y plus z. This is my bend congruence, the bend relation, and I can always construct the bend congruence, which is take the transitive closure of this. Okay, so why is this meaningful in any way is because it sort of abstracts or captures the minimum attained at least twice somehow algebraically. And also it has a it's geometrically meaningful, which means that the T points of this thing, which is supposed to play the role of an affine tropical scheme, the spec of an affine, of the coordinate ring of an affine tropical scheme, are actually the honest tropical variety. So in a way, this is geometrically meaningful in the sense, so here's a theorem, and the theorem says, let I be an ideal, then the dimension of the tropical variety, which is this, again, a polyhedral complex, is the dimension of this coordinate ring -1. And why is this -1 happening here is because the dimension of T is 1 and it offsets everything by 1. So in fact, not only do we pick out some algebraic meaningful algebraic dimension, but we also recover the geometric dimension this way. And in the end, I want to say one more thing about computing dimension via the Hilbert function. And this is related to work of Diane McLagan and Philippe Rincon. So ideals of this type that I discussed, which are trop I, they are referred to as tropicalized ideals. Not every ideal comes in from here. They're also a proper subset of something a little bigger called tropical ideals. So tropical ideals have this shadow of subtraction that the tropicalized ideals do, but tropical ideals can abstract it a little further, and it's a strictly bigger set. And not all of them come in this form as a tropicalization of something. They are very nice, and they're nice in the following way. They are almost never, well, this is probably not the nice thing, but they have a lot of combinatorial properties. They look like matroids in each homogeneous degree, and so on. But let me tell you something about these ideals. So these tropical ideals are almost never finitely generated, which is crazy and sad and makes them very hard to work with. However, they do satisfy an ascending chain condition. And this is something that we'll talk about in a second. The congruence bend of a tropical ideal is also almost never finitely generated. However, the variety of such a thing is cut out by a finite set, which is called a tropical basis, which is nice. And moreover, in McLagan and Rincon prove that the Hilbert function, in fact, the Hilbert polynomial of the original ideal, which is an ideal of the ring, and the ideal of the semiring actually agree for these tropical ideals. So in this case, Hilbert function, Hilbert polynomial makes sense, and then they agree. And perhaps the question is, how does our thing relate here? And because of all these equalities, and because of this last point, the degree of the Hilbert polynomial will really, defined in this way, will be the dimension of the polyhedral complex and the cruel dimension, perhaps -1, that we introduced here. And I think I'm going to stop here, and thank you for your attention.
Okay, thank you very much for the nice talk. It was something new for most of us, I think, but nevertheless, it was quite amusing, quite interesting. Do you have some questions? Andrea raised hand, but I don't know. If you have any questions, you simply ask them. Or comments?
Well, I think that you have that all the time. Where the name comes from?
Oh, okay. So the name comes from a Brazilian, or rather Hungarian, then later Brazilian mathematician who was working in optimization theory. And after he passed away, his French colleagues decided to somehow commemorate him by calling what he was working with a tropical geometry. He was working with min plus algebras. And that's sort of how the name came. Yes, it has very loose connection to the tropics.
Mm-hmm. Okay. But he must have had something in mind. Who knows?
I don't know. I think it's just people kept it because it's catchy.
Of course.
And,
yeah. But it's interesting too. So it's not only catchy.
Okay, if you give a name of something, this name should be in such a way that if you have something to sell, you should name in such a way to sell it.
Indeed.
Also, probably we should wait a little bit till December or January to give you for your talk, when it will be colder than now, because now it's 16 degrees in Sofia.
Oh.
And if it's -10, it will be much better to have a tropical talk.
Indeed. Warms up the heart.
Maybe I should organize a conference here in the tropical part of the States. Would you come?
For sure.
Okay. Well, I'm thinking about it, by the way. It's not clearly in my mind well, but maybe I would do something next year, 2022. Florida is open anyway, so yeah, hopefully COVID will be even in a better situation, and then we'll see.
For us, it's ending. They are allowing us without masks from today inside.
Uh-huh. And they're putting us in the rooms already without asking. I have been teaching for 2 years only online. Now I have to go into the room because everybody's going into the room. Practically no online courses anymore.
Oh, we didn't have online courses. We were in person. We were doing hybrid.
Oh yeah, all right.
Okay.
I had my online
Are there
courses.
some other comments or thanks or questions? If not, just thank the speaker once again. And now we can continue in Bulgarian simply for chat. Also, the other people, if they want to say something, they can do this in other languages.
I will stop the recording now.